Okay, YouTube, in this video we're going to focus on how we describe the domain of a function. So let us recall that the domain of a function is the set of all inputs for a function, or x values for a function. So we refer to these domain values as input values. And because often what we do is we use a function or an expression or a rule, okay, to define how we take the x value and get to the y value. What's going to happen is sometimes we're going to have expressions that when you plug in a specific x value, it just simply doesn't work, and so therefore we would say that we would exclude that from the domain. So we can see here that the domain of a function can be described explicitly, or it can be what we call implied by the expression used to define the function. So this rule that I'm talking about here that sometimes maybe restricts some x values, what we talk about when we mean implied domain is we're implying which values of x could not work just by looking at this rule. What could you imply? It's kind of like when I give blood. I'm a gentleman. And they asked me that question, are you pregnant or anything like that? I just click on the option, I am a male, because they imply that I am not pregnant. So if I were to look at, say, some expressions like these two you see here, f of x equals 1 over x squared minus 4, and f of x equals the square root of x, which values of x could I imply would not even work in this in the first place, or what would be my implied domain? So in terms of the domain, first things first, we have to exclude all x values that result in division by 0. So we exclude all x values that result in division by 0 because division by 0 is undefined. So what we want to do here is we want to find what are all the x values that would cause us to divide by 0. So if there's ever an expression in x in the denominator of a rational expression, then what we're going to do is set equal to 0 and solve. So we're going to find all of the x values that would cause the denominator to equal 0 in the first place. X squared minus 4 equals 0. We could add 4 to the other side. We get x squared equals 4. And then taking the square root of both sides, this is pretty important because you took the square root. You need to put a plus or minus out in front. But we get two x values here for which this function does not even work. So as a matter of fact, what I'd like to point out here is I went and graphed this in Desmos, 1 over x squared minus 4. And you can clearly see here that if I were to graph a vertical line x equals 2 or the vertical line x equals negative 2, you can see these two lines here. Maybe if I modify them and we'll make them dotted here, these asymptotic lines. And I'll make them both red. You can see these are two x values at which our graph doesn't even have a y value. And so the implied domain of this, we could just write it out here, would be all values of x. And then we'll put a colon here, and we're going to say such that x cannot be equal to plus or minus 2. So in terms of the domain, we could list the domain as being implied as being all x values, but not plus or minus 2, because you can't divide by 0. It's undefined. So for this next example, you look at this, you see a radical. And so I want everybody to recall that when we talk about a square root or a fourth root or a sixth root, it is impossible to take a number times itself, okay, an even number of times, and result in a negative. So for any values of x that I put in here that are negative, I'm not going to get a y value that comes back because there is no number I could take times itself and get a negative. So we say that domain should always exclude x values that result in even roots of negative numbers. And so the way this works is this. We're going to take the radicand, we're going to set the radicand. This is the inside stuff on a radical, greater than 0 and solve. Okay. So the way this works is we're going to take everything that's in here, in this case x, we're going to just say greater than, in this case, or greater than or equal to 0. It can be equal to 0. But we're going to solve this for x, and the neat thing about this is it's already solved. And so we're going to say the domain then is all x values, all x greater than or equal to 0. Okay. So now this is going to look a little bit different this year. Let me go ahead and show you this graph as well. As a matter of fact, our square root graph. You can see that if I graph it here, it looks like this. And in terms of x values, you can see that no x values to the left of 0 ever give us a y value, but as I continue to go to the right, okay, I always get the square root of some positive number or the square root of 0 to work. And so since that's the case, we're going to say the domain of this, since we said is all x values greater than or equal to 0, I want to start using a new notation sooner or later, so I'm going to introduce that a little bit here. We could say that this is the same as the x interval, okay, an interval of x values that we list this way. We say from 0 and going out forever and ever till you get to infinity. So the way this works when I wrote my domain here, you're not going to have to pay, you're not going to have to know this instantly after this video, but it's good to know this is a bracket here, and this bracket, okay, bracket means it includes the endpoint of that interval. And then the parenthesis, so parenthesis means up to but not including, basically. So when we look at something like this, we never include infinity since it's not a number, but we're saying starting at 0 and including 0 because it has a bracket and going out to infinity, that would be the set of domain values for this function here. Okay. So keeping these things in mind, let's go ahead and take a look at what we would imply as being the domain for each of these functions you see here. So for letter A, this is kind of neat. We have this written out as a set of input-output pairs. And so in terms of the domain, we could just list this as a set of numbers here, and it looks to me like -3 is in the domain, -1 is in the domain, 0 is in the domain, 2 is in the domain, and 4 is in the domain of this function. So we're looking at the domain values here, and they've also listed range values here. So let's list those. We say range. And we're also going to list this as a set of numbers. We say 0 was mapped onto, 4 was mapped onto, 2 was mapped onto. Now I notice that 2 is listed here twice, so I don't have to list it again since it was included in the domain. And then we say -1 is mapped onto. So our domain and range for something that's listed in this notation, we can just list the x's, list the y's. Now for letter B here, what I notice is that we have an expression in x in the denominator. So for letter B here, what we're going to do is we're going to take this g of x, and we're going to take the denominator, okay, and set it equal to 0 and determine what would be the x value that would cause this to be true. So solving for this just by subtracting 5 to this side, we can see that if x is equal to -5, then this is going to be undefined. And so in terms of the domain, we'll say all x such that x cannot be equal to -5 would be a sufficient way to list the domain of this function here. So letter C. Now I like letter C because it says the volume of a sphere. And what we see here is that this isn't y as a function of x, but really we have volume as a function of its radius. So we could relist this equation this way. But what makes this equation particularly interesting is this. When you talk about a sphere, our radius is just not going to be negative. It's always going to be positive. So the volume of this sphere would have to have an r value that is greater than or equal to 0 because radius is non-negative. Okay. And so for letter D also, let's take a look at letter D here. What we see showing up here is a radical, and not just a radical, any radical, we have an even radical. So we can't have negatives in here. So what we're going to do is we're going to set the radicand, okay, greater than or equal to 0 so that it's non-negative, and then we're going to solve for what x values satisfy this. And so let's go ahead and do this here. We say 4 minus 3x. We want this to be not negative. So let's go ahead and subtract 4 from both sides here. We get -3x is greater than or equal to -4, and then we're going to divide both sides of this by a -3, which, if you're remembering from your algebra, when you take an inequality and you divide by a negative, what that means is we need to switch this middle sign over. And so we get a positive 4/3 here. So the way this would look is we'd say the domain here would be all x values less than or equal to 4/3. And in interval notation, we would write this really as to the left all the way up to and including 4/3 because it wasn't or equals to, but it stops there. Only x values to the left of that will work. So to find domain, keep these techniques in mind. Cheers.